Okay, we have here the square root of 33 plus square root 300 plus square root 500 plus square root of 60, and we're asked to simplify this. Well, sometimes it's hard to know what that means. Maybe the best way to simplify it is just to leave it the way it is. Well, I'll tell you though, there is a way to remove the outer radical, so I guess we'll consider that simplified. So I've done a few problems. I did an integral that was kind of like this with the nested radical. The strategy I used in that integral is what we want is this, everything in here, if it's a perfect square, that's going to allow us to get rid of the outer radical and simplify it. So the way I've done this before is if we have something like square root of a times square root of b, when you square this, you get a plus b, multiply out the middle terms, and you get 2 square root ab. Well, the thing with this is it doesn't really match what we have in our radical. I mean, this is going to be a non-radical, so this kind of like could match with our 33. And then we've got a term that potentially is like one of these, but then what about the other 2 radicals? Well, what we can do is look at our formula. Instead of just 2 expressions, instead of just 2 radicals, we can look at square root of a plus square root of b plus square root of c all squared. And then expanding this out, now we've got something that potentially could work. If, say, a plus b plus c, if that's 33, well, we've got 3 radicals. We don't have the 2, but we could probably make that happen. So this looks like it could work. One alternative that you can look at for these kind of problems, I've done it this way in the past, is have one term be a non-radical. So something like this, when you square this out, it's going to look a little different. Doing it this way, same kind of thing where we want just this thing now to equal 33. But then with the radicals, we need to pull a 2 out, but we also need to pull an a out of the expression as well. So I think the way to start with it is get rid of this because we don't need that. But if we can start rearranging this expression, maybe we can see which formula works better. So we'll just leave the 33 for now. For 300 is going to be the same thing as 4 times 75. And so this thing's inside a square root, but 4 is a perfect square, so I can write this as 2 square root 75. So we'll do that here. Now, same thing with 500, where 500 is 4 times 125. We know 4 is a perfect square, so we'll just kind of do it on the fly, and we'll write this as 2 square root 125 for square root 500. And then for square root of 60, I can write that one as 60 is 4 times 15, so that's going to be 2 square root 15. So now what we have here, this matches this first one here. We've pulled a 2 out of everything. That looks good. But notice, now we could have done this one as well, because here we've got like 25 in common. This is 75 is 25 times 3, 125 is 25 times 5. So we could pull out the 25. 25 is a perfect square, so we could pull a 5 out of each of these if we wanted to use the second formula. But I think we're in good shape to just use the first formula here. So let's get rid of this one, and we'll just use this middle formula here. And so I think all we need to do is figure out what our a, b, and c is. So I'm not sure if there's different ways to do it, but this is the easy one for the prime factorization. So 15 is 3 times 5. And so that's our b times c value. We don't know what order is what. Here, like this we can write as 125 is the same thing as 5 cubed. So I'm not sure how to break that up yet. And then here, 75 is 3 times 5 squared. So if we have 3 variables, a, b, and c, one of them I think is going to be 3. Doesn't mean because they don't have to be primes, right? So we're not quite sure. But let's see, another one could be, we don't have a 5 squared here. So like another one's going to be 5, and then another one has to be 5 squared. What I can do is rearrange this right here. Instead of writing it as 1 times 5 cubed, let me just write this one as 5 times 5 squared. And then let's put some labels on things, so let's see what's going to work. I think a should be 5 squared, and then b, kind of just lining it up with this. So to get a times b here, we'll call b equal to 3, and then that's going to leave c, so c is going to be 5. So we'll have c here, and this will be b. And so this is going to exactly match our formula. But one thing we need to check though, does this really work for a plus b plus c? So we're saying a equals 5 squared or 25, b is going to be 3, and c is going to be 5. Adding that up, a plus b plus c, 25 plus 3 is 28, plus 5, 33. So let's see if we can finish this whole thing off. So we're actually we've got our expression inside the radical in this form over here. And so we'll just go backwards with the formula and put it in this form. So this whole thing is gonna boil down, everything's inside the square root. We're gonna have square root of a, which is 25, which is gonna reduce square root of 3 plus square root of 5, all squared. But we can cancel the radical with the square. We don't need absolute value, everything is clearly positive. And so we can just reduce it. Square root of 25 is 5 plus square root of 3 plus square root of 5, and that's it. Okay, so there you go. Good times with the nested radical. Thanks everyone for watching. Have a good day.